Hi, I'm Emma. So I work at the Bureau of Meteorology, and I work primarily on our convective-scale regional climate downscaling project, which is called BARPA. And this is coming out of the Australian Climate Service, and so thanks to all my co-authors on here. And I'd like to point out that although I'm talking entirely about the UM in this instance, most of what we will be doing is a multi-regional climate model approach where CCAM will be doing very similar simulations as well. And so Marcus Thatcher is leading that work. So our motivation here is we're looking at Australia's climate is very variable with many extreme events. We're focused around the need for robust fine-scale hazard information over Australia, and that's Australia's changing hazards, and making hazard projections. So the convective scale we heard a lot about in Tomoki's talk just before. We are explicitly representing some form of vertical motion, which may not be perfect because we are quite coarse resolutions, but it does lead us to believe that we will have better representation of convective hazards, particularly like thunderstorms and tropical cyclones and things like that. Something that's particularly useful or interesting about this is that we expect these models to better represent short duration, high intensity rainfall. And that's something that has been observed to be diverging in the real world between coarse resolution models and observation. So if you think of Cyclone Jasper earlier, or I guess last year, there's been some unprecedented rainfall totals over very short durations in recent years, and that's a trend that has been shown in many studies not to be really gotten well by convection parameterized models. So the Australian Climate Service wants to be ready to be producing climate hazards at convective scale when we downscale CMIP7. And in order to do that, we need to do some research and development to have reliable CPM projections, or CPM models, which work in climate mode as well as weather mode. So today I'll talk about our experimental design for these BARPA-C experiments. I'll go through one particular issue that we've been grappling with recently, and I should say I find it more interesting to talk about the things that go wrong than the things that go well. So there are good things here as well, and I'll try and talk about the places we are seeing improvement as well. So our experimental design, again, we're working with the Met Office Unified Model in the regional configuration. So we're nesting within global climate models or reanalysis, depending on our application. We nest within reanalysis to evaluate our models, and we nest within global climate models to create projections. So today I'll only really talk about nesting within ERA 5, and that uses BARPA-R, our existing projections that are all published and complete, as an intermediate nest. We do want to be looking at, and so I've got this table here, we've got 2 evaluation runs driven by ERA 5, and we've got 2 GCM-driven runs driven by ACCESS, ESM 1.5, and EC-Earth as the GCM runs, and there'll be 10-year time slices we hope to have done by the end of June next year. So the first thing to talk about here is this dry bias we're facing, and our attempts to fix it using spectral nudging. So we did our first 10-year run, similar to the sort of setup that Shamel was talking about. We just take our atmosphere-only Joules UM-coupled regional model and push some model data in the sides. We run that for 10 years. And what we find is that we get this quite strong dry bias over northern Australia and the mean state, which is coming out as a reduction in the length of the wet spells that we get. It's also associated with a shift in the monsoon shear line, so that was shifting northwards. Too few tropical cyclones were forming in northern Australia, which is quite concerning considering we have this hazard focus, drier soil moisture and some other things. Now, this northern Australian monsoon is quite a strongly coupled system, and so the circulation and the rainfall is quite coupled, so we don't know, are we having less rainfall because we have less monsoon winds, or are we having less monsoon winds because we have less rainfall, or is these sort of forming a model drift and causing each issue feeding off each other? So a circuit breaker we were able to introduce was this spectral nudging, and that was able to constrain the model, the convective model to its boundary conditions, or to its driving model more strongly, and so we use this just constrains the large length scales while allowing the smaller length scales to run free. So we implemented that. I won't go through too many of the details of the maths here, but we've got quite a soft nudging that we landed on using at the end, and sort of a 1,500 kilometre length scale where we nudge above. We found it did improve the location of the monsoon trough in our simulations, so we're comparing the orange and the red here. The orange is the driving model, the red is the downscaled model, and we can see that that monsoon trough has shifted south compared to the issue, which I didn't show before, but that's the blue line where the monsoon trough is quite far north. And we found that looking at more than just the mean state as well, but just for simplicity I'll show you that. And then also looking at the cyclone track density, we do see a resolution in the cyclone frequency. So you can see there's a lot of red down in the difference between IB tracks frequencies here and our free run. When we spectrally nudge, that resolves. And the counts generally are looking quite good everywhere, although we do have a strong bias there. That's something unrelated. However, we found the mean state precipitation was improved over the ocean and not really improved over land as much at all. Interestingly, for the comparison with Shramana's talk just before, we find that our dry bias emerges after about 5 years. So this plot here in the bottom right shows the accumulated rainfall over northern Australia over land only, and we can see we were tracking pretty well up between 2013 and 2017 or so, and then it goes off the cliff. Okay, so I've got 2 minutes. Okay, I'm a bit behind because I did want to talk through this. So our hypothesis of why we might still be seeing this dry bias, there could be some land surface feedbacks going on. We do expect to have less rainfall infiltration when we have more intense rainfall. And we have also made some changes to the land use types, which we will try to revert and see if that changes anything. And also the representation of shallow convection. So I'll leave you to think about Tomoki's talk before, because that was really a good demonstration of what we're not including at 4 kilometres. There are some scale-aware convection schemes under development that we'd really like to test as well. So just to look very quickly at the added value that we do see, and this is coming back to that short duration, high intensity precipitation. So this plot here shows the maximum, so average over 10 years of the hourly maximum rainfall in that whole year. So it's quite an extreme statistic. So we can see that it's quite different between our BARPA-C and BARPA-R, comparing these first two panels first of all. And we have this band of greeny colours going down the east coast, and also these reddy colours in northern Australia, showing the regions where we do have this really high convective rainfall likely to occur. And then just that's not really present, that spatial pattern isn't present in BARPA-R. When we just look at station locations, and this is a new ish or newly QC'd data set of hourly station locations across Australia, you can see just an eye-to-eye comparison between BARPA-C and the observations is remarkably good. And then BARPA-R is not doing as well at all. We see similar improvements when we look at radar rainfall. We also see better cyclone dynamics, we think, although we do have a few too many cyclones. This is my very dodgy algorithm that should be replaced by something better soon. But we're starting to see eye walls forming as well. So in summary, we're developing BARPA-C. We've still got some issues, but we are seeing improvements in short duration extreme rainfall, and we're taking the time to investigate and see how much better we can make this model. The other thing to say is that because it's not really impacted by model drift, our sister project, the BARA reanalysis, is doing really well. It's actually published, so I'm going to leave a slide up with some details of how BARA is at the moment. So please use it.
Thanks, Emma. Just wondering if you went to more like monthly statistics of rainfall on those station data, would it look pretty much similar with BARPA-R and sorry, I got my terms wrong. But the R and the C, do they look more or less similar if you don't choose the really extreme statistic?
Yeah, so I think they do. So they look. The C looks worse, obviously, when you look at the mean, the seasonal mean, because that's where we're seeing the dry bias. If you go to less extremes, I think the P99 was fairly similar, and then it was above the P99 that we were seeing big improvements. And you can kind of see that. Well, yeah, so at daily rainfall, it was, C was slightly better, and at hourly rainfall, C is much better.
So your model bias got worse from 2018-ish onwards or something. Does that mean the character of the monsoon changed then and the model's not picking it up or something? Or?
Yeah, I'm not sure. I did have a quick look into something like that. It is, 10 years still is not very long, I guess. It's very expensive, but it's not very long. But it could be that, but it could also be a sort of a model drift that's only really becoming apparent after 5 years.
Have to be really deep soil moisture or something then?
Yeah. So we've been looking into the soil moistures. We need to look into them more.
Claire, after Claire, we're going to finish up.
Thanks, Emma. So you found that the spectral nudging improved the rainfall and the monsoon bias. Were there any other aspects of the model variability that the spectral nudging actually made worse in terms of suppressing any part of the variability?
We couldn't see any, and we initially used a much stronger nudging, and we found that spun up all sorts of very, very low pressure cyclones, and we had very high extreme rainfall. But when we went down to the 12-hour nudging, we haven't seen any degradations, I would say.
Thanks very much, Emma.